Hello again. So today we're going to be talking about enthalpy, which is also known as H delta H. We also think of that as just heat. It's really heat energy at a constant pressure. And so we kind of use it interchangeably, the word heat versus enthalpy. But the units for enthalpy are usually in kilojoules, and again, it's at a constant pressure. So let's get started. So here is a place where we have enthalpy of reaction. Reaction, RXN, is the abbreviation for reaction. And to calculate the heat of a reaction, we can subtract energy of products minus energy of reactants. Enthalpy of formation, or heat of formation, is the amount of heat energy it takes to form 1 mole of the substance from its elements. And we can get that, for instance, for this substance KBr. So if we were going to form 1 mole of KBr from its elements, it would require a mole of solid potassium, that's how it naturally occurs, plus half a mole of bromine liquid. Because of Hofbrinkel or Brinkelhoff, bromine occurs naturally as Br2, but we only want 1 mole of Br for the KBr. So it'd be half a mole of Br2 liquid plus a mole of potassium solid, and that's their naturally occurring states. Combining those, we would get 1 mole of KBr. And so the amount of heat that is required to form that 1 mole is called the heat of formation. And there's charts that give the heat of formation values for many substances. We have a chart in our book on page 975, but you can also find charts online. And for any naturally occurring substance like O2, H2, or the metals, that heat of formation value is 0. They're already formed, so you don't have to put heat in or get heat out when they're formed. So taking a look at a chart, you can see for silver, for instance, naturally occurring, its value is 0. But for silver chloride, which is a solid, when 1 mole of that is formed, it will give off 127.068 kilojoules. So for 1 mole of that, that's how much heat's given off when it's formed. Versus silver cyanide, it requires an input of 146 kilojoules for 1 mole of it to form. So the negative values, as before, mean that much heat is given off. The positive values mean that much heat is put in when 1 mole of it is formed. So we'll use this chart to look up the values for our products and reactants, and then we will be able to calculate for reactions how much heat overall is either taken in or given off by that reaction. Okay, so our equation then to calculate the heat for a reaction is the sum of, that's the sigma, capital sigma sign, it means sum of, the sum of the heats of formation of the products, that's SUM, sum, the sum of the heats of formation of the products minus the sum, SUM, of the heats of formation of the reactants. So we're going to just use the values from a chart. Again, these are values for 1 mole of the substance. So in a balanced equation, we have to multiply by the number of moles in the balanced equation. And we can calculate the heat of reaction for any reaction as long as we have those heat of formation values. So for instance, for this one, I would need to have the heat of formation for NH3 as a gas, and it's important to note the state of the matter too. There could be different ones where maybe, for sure for water, it lists water as a liquid and water as a gas. So make sure you use water as a gas. So always pay attention to the state of matter for the substance as well when you look up the values. So on our chart, we'll look up the value for NH3 as a gas, but we'll have to multiply that by 4. We'll look up the value for oxygen as a gas, but it'll tell us it's 0 because it's already naturally occurring. And then we'll look up the value for NO as a gas. We'll have to multiply that by 4. And we'll look up the value for water as a gas, and we'll multiply that by 6. Okay, so here is example problem. Let's kind of take it step by step here. So first step is to look on the chart. So I looked on the chart and I found the heat of formation for ammonia NH3 gas to be negative 45.9 kilojoules per mole. Then I looked up the value, again, oxygen is 0. I look up the value for NO gas, and it's 91.3 kilojoules per mole. And I look up the value for H2O gas, and it's negative 241.8 kilojoules per mole. So then products minus reactants. So this is something that people do backwards a lot of times, because in the balanced equation, the reactants are given first. But you have to write the products values when you do this equation. So the sum SUM of the products minus the sum SUM of the reactants is what I'm looking for. And then again, don't forget to multiply each by the number of moles. Okay, so I look to my products. I have 4 moles of NO, so 4 times 91.3 kilojoules. And then I have 6 moles of water, so 6 times negative 241.8 moles. That's my products. And then I add those together, and I subtract from that the sum of the reactants, which I only have one reactant value because oxygen 0. So 4 times the value for NH3 is 4 times negative 45.9. Those are all in kilojoules. So I multiply by the number of moles. I add up the products. In this case, I only have the one reactant. I multiply by that, and I solve for that, and I should get negative 1085.6 for the products minus negative 183.6 for the reactants, for a grand total of negative 902 kilojoules. So this is the heat of reaction. How much heat, in this case it's negative, how much heat is given off by this reaction when this reaction happens. Okay, let's look at another one. If I want to calculate the heat of a reaction for 2 NO gas plus O2 gas making 2 NO2 gas. Once again, I look up the value for the NO gas, the heat of formation value off the chart. It's 91.3. Oxygen is still 0 because it's naturally occurring. And then the heat of formation value for NO2 gas is 33.2 kilojoules. Again, I need to basically flip that because I'm doing products minus reactants. So I need 2 times the value of NO2 minus the sum of 2 times the value of NO plus O2, but again, O2 is 0. So it will just be 2 times 33.2, the value for the NO2, minus 2 times 91.3, the value for the NO, and I multiply and subtract that, and I get negative 116.2 kilojoules. So once again, this reaction is giving off this much heat because it's negative when the 2 moles of NO reacts with a mole of O2 to form 2 moles of NO2. A little bit of a variation would be, maybe I'm given the heat of reaction overall, and I am not given one of the values for something in the reaction. Like in this case, I'm not given the value for FeO. So that would be my unknown, what I would be solving for. It's the same setup. It's products minus reactants equals the heat of formation, the heat of the reaction. But I have the heat of the reaction in this case. So I would be able to plug in the value for iron, which would be 0 because it's naturally occurring. I can look up the value for CO2 gas, or I would be given that and plug that in. I can look up the value for CO and plug that in. And then what I'm missing is the value for FeO. So that would be my X. and there's 2 moles of it, so it would be 2x. So then this would just be an algebra problem where I would have all the values except for this one, and I could then solve for that value. So that's just a little bit of a variation. So that's how you can calculate heats of reaction by using heats of formation.